Okay, let's get started. This actually is the last lecture day, live lecture day, except for Monday, which is kind of a special day. And so we'll have breakfast on Monday, and that's it. You got to buy your own, or you might as well just leave out some of the snacks and stuff and see if they want to take them, and find some place to store them for yourself or something. Because we still got a fair amount, right?
Yeah.
Okay. You ready? Okay, last time we talked about X-ray and ultrasonic testing, and ultrasonic testing is replacing radiography and weld inspection in general. It has been for about 10 years due to easier scheduling and lower costs. And the primary thing of lower costs is you don't have to clear out the whole fabrication facility because you're going to have high-intensity radiation. One shipyard study found that the X-rays cost 10 times as much as the ultrasonic tests. And the primary reason is because they had to have like 6 or 7 people just located at different places around where you're doing the radiograph to make sure nobody inadvertently walks into an area where radiation is. So just safety, people standing there, safety watchers, safety monitors. Actually, there was a student in this class who had done the study when he was in a naval shipyard out on the West Coast, and he showed that it was costing 10 times as much to do X-ray inspection versus ultrasonic. And one of the reasons he did this was a government shipyard. Most of the commercial shipyards for the U.S. Navy had switched over to ultrasonics as soon as the Naval Sea Systems Command said you could, in terms of weld quality. But the public shipyards, the ones owned by the government, have been reluctant over the last 8 years to do this because they said, oh, it's not really cheaper. They had all kinds of excuses. But it's sort of the government's not willing to save money, okay? But the commercial shipyards that are owned by companies switched over almost immediately. Planar flaws have to be inspected in the most favorable orientation for finding them. And I put up this overhead showing that for X-rays, if you have a planar flaw in this orientation, it's hard for the X-ray to see it because that orientation isn't as large a fraction of the thickness as this orientation. However, what you're really interested in is a planar flaw that's oriented in the direction of the maximum principal stresses, or any major principal stresses. And remember, you got stresses and stress is a tensor, but if you're talking principal stresses, you're talking about 3 dimensions, right? X, Y, and Z coordinates. And any dimension or any direction in which you have a very large stress, then that's where a planar flaw is liable to progress into a crack. And so you have to be careful about that. That's true both for X-rays and for ultrasonics. If you come in with an ultrasonic beam, the beam has to bounce off a planar defect as if it were a wall, or a planar flaw as if it were a wall. And if the wall's oriented that way, the beam's coming this way, it's not going to give you much of a reflection. You want it oriented in the proper direction, which is exactly the opposite direction from X-rays. X-rays, you want it oriented this way rather than this way because you're measuring the change in intensity or thickness of the flaw. So in X-rays, you'll get the maximum thickness in this orientation. In ultrasonics, you'll get the maximum wall reflection in this orientation. So it's sort of the opposite. But trained operators generally are experienced in what type of orientations to do these things. Okay. Anybody have any questions from last time? If not, let's talk a little bit more about, well actually, there's one thing I forgot to talk about in radiation. There's lots of different measures of radiation and they can get a little bit confusing. One is the Roentgen, which is just a unit of radiation. And it's a 1 electrostatic unit charge in 1 cubic centimeter of dry air at standard temperature and pressure. And that's, in energy, that's equal to 83 times 10 to the minus 4 joules per kilogram of dry air. So it's basically radiation that will create or has the potential to ionize air under those conditions. And so it's a measure of the intensity of the radiation in terms of its ionizing ability. Because we're interested in ionizing radiation. Ionizing radiation is the radiation that can do damage to living tissue. Obviously, we don't care about the radiation in terms of its damage to non-living tissue because, we do in some cases. There's radiation all around us, and I already mentioned if you fly to Denver, you're going to get more radiation than if you go to the doctor and have a chest X-ray or whatever, by a factor of 4 or 5 or something like that, if I remember. In fact, it may be a factor of 10 now, as they get better and better detectors. But there's cosmic radiation all the time, and so it's not as if very low doses of radiation are causing severe damage in living organisms. But the radiation that surrounds us also causes damage and changes in other materials. I remember when Professor Ogilvy taught me about X-ray diffraction and stuff, he told the story about having been at Canterbury Cathedral or somewhere in Britain. This was like a 12th century or 13th century cathedral, and they had the stained glass windows, and the person at the cathedral basically was giving the tour, and they said, and we have this rose-colored glass up here in the stained glass windows, and the greatest scientists in the world have not been able to reproduce this wonderful rose color that the artisans of the 13th century had produced. Well, Professor Ogilvy knew that anybody can analyze the composition of glass and could reproduce the composition of the glass. And he told her that, well, that wasn't, and that she was going on about the beautiful color that 13th century artisans had produced. He says, well, that wasn't the color that they had produced in the 13th century, because it's been getting cosmic radiation for 7 centuries. And in fact, the color of the glass has changed, because in glass, the color of the glass is a very strong function of the defect sites. And so you have some cosmic radiation, you knock some ion out of its position in the glass, you end up with something just like in a semiconductor. You change the electrical charge in the way it absorbs light, and so the color had changed. Well, this curator didn't particularly appreciate the fact that he said he could reproduce it within a few days, because all he had to do was make the same composition glass and stick it in an accelerator and radiate it, and eventually he'd get the same color. It turns out that became, a few years ago, a problem as people learned how to artificially irradiate things for diamonds, because certain diamonds, when they're initially formed, if they don't have lots of impurities and inclusions, should be clear. And it turns out, in most cases, the clearest diamonds are the most valuable diamonds, but there are a lot of yellow diamonds out there. Well, the yellow diamonds are because they're older diamonds, and they've been getting a lot of cosmic radiation. They've started out clear, more likely. Some of them have impurities in them and gives them color, but a lot of them is just because they're older, geologically. And people learned they could take different colored diamonds and irradiate them, and some colored diamonds, like pink and blue and stuff, actually are more valuable than the clear. And so people were artificially irradiating diamonds to try to change their value. And there's laws against that, but I don't know if it should make a difference. I mean, just because you're accelerating a natural process, why shouldn't you be able to do it? It's just processing of your material. But I guess the people who dig diamonds out of the ground didn't like it. Anyway, Röntgen is a measure of radiation, essentially ionizing radiation, which does damage to living tissues. The rad is the absorbed dose. And typically, if you go in and, for example, I had cancer treatment 7, 8 years ago, and I had to go in and get radiation on my neck. They gave me, they talk in Xrays, which is the SI unit. A rad is 1/10 of a joule per kilogram of the body weight in the area, and the Gray is 10 times as much, and it has the SI units. I can't remember what a typical, I think I got 400 Grays, something like that, which would be like 4,000 rad here. Didn't have to shave over there for a while. And then there's also the Röntgen equivalent man, or a REM, or sievert, and this is basically a measure of the Röntgen as absorbed by a human being. Okay, different insects and stuff will be damaged in different ways. So this is trying to measure some sort of biological equivalent of this amount of, if you want, ionizing energy. So this is taking the energy and applying some biological correction, and it's basically developed by experimental procedures. You don't obviously intentionally radiate people, but sometimes you can quantify when someone does get radiated. They can quantify how much radiation they got, and they can estimate the damage to the person. There's something called relative biological effectiveness, and you can go look for different types of living tissue and find out, I mean, different tissue in different parts of the body. Bone reacts differently than muscle to things. Also, the type of, the energy of the radiation sometimes has an effect. So there's this other term. There's also, getting back to a more purely scientific, physically scientific rather than biologically, radioactive disintegrations, which is the Curie. Should have parentheses on there. 1 Curie is equal to 3.7 times 10 to the 10th becquerels, and a becquerel is 1 disintegration per second. So if I have 1 atom disintegrating per second, and I have 3.7 times 10 to the 10th of those atoms disintegrating per second, I'll have 1 Curie of radiation. So you typically, if you're talking about cobalt-60 or iridium-192 as a radiation source, you'll be talking about how many Curies of that material you have. And that's just telling you the intensity of the radiation that's coming out. So those are some of the terms, and I just kind of went through them because you might hear these things and you don't, they're all different. It's just different measures of different things. A couple of them are physical measurements of ionizing energy or the number of disintegrations. Others somehow try to measure some sort of living tissue response to that radiation, which is what you're really after in the long run, which gets a little fuzzier about what that really means and how you measure it. Okay, we were then talking about ultrasonics, and I showed the pitch and catch technique and things. Basically, ultrasonics come in and reflect off the back wall, and then I mentioned this case of this big forging out in Seattle, where the guy actually found it by ultrasonics. I told him the story about how his boss threw him out of the office, and they shipped the part and it later failed. But there in the records, there was the big defect sitting there in the records. It turns out ultrasonics is even more complex than radiography in terms of the experimental technique and trying to analyze it. For example, this is just showing on this side that I might send off a pulse from my piezoelectric transducer, but the pulse would look something like this in time spectrum. And that can be deconvoluted, in this case, to a 1 megahertz pulse, a 1.2 megahertz pulse, and a 0.8 megahertz pulse. The transducers are not perfect in frequency. Okay, they have a distribution of frequencies. You're basically sending out a pulse. It's a piezoelectric transducer, so you can put a pulse of electrical energy in. You'll get a pulse out. The pulse may look like that, but if you do a Fourier transform, or actually if you take these 3 pure pulses and do combine them, you'll get this. If you do the Fourier transform, you get the inverse, right? In any case, this is sort of an idealized with just 3 components. Then sometimes people will describe that in a rectified way. Pulse looks like this, and sometimes they'll just smooth the whole thing over and say, this is the width of my pulse. You have to ask yourself, when someone mentions something like that they were talking about in a time domain, it's not frequency this time, in a time domain, they might talk about this width of the pulse, whereas in fact your individual waves are shorter things in time, and this is just a packet smoothed over the top of all of that. Over here, turns out both with X-rays and ultrasonics, ideally you would like to have an infinitely sharp point source, because you just think of a camera in optics. You know, if you have a finite size source, you have radiation coming from a distribution, and that causes fuzziness, lack of focus when you're imaging whatever you're doing. You have the same problem with ultrasonics and with X-rays as you do with photography in terms of not having a perfect point source. You know, you can get the greatest depth of field in a camera if you stop down the lens to a longer, higher f-stop. Well, you have those same types of things, and delta here for ultrasonics is the width of the source. Now for X-rays, you can get the sharpest sources if you go to typically accelerators, electrically, you know, 200 kilovolt electrical X-ray tubes, or linear accelerators that give you a megavolt or 2 megavolts, which you need if you're going through 4 to 6 inches of steel. If you start using isotope sources like iridium-192, they have a finite size, and their size is typically larger than the electrically generated X-rays, and therefore they're fuzzier pictures. So the field X-rays are always not quite as sharp as the ones that are typically done in the laboratory with these electrical generation sources. At one time, some people had developed, at one of the national labs, they had a laser weapon, and they found that they could shoot the laser into the surface and vaporize a little bit of gas above the surface, and then hit it with another pulse of the laser, and they take that gas that they just vaporized, and this is all within nanoseconds, right? They'd hit it a second time, and they would superheat it, such that it would give off actually X-ray radiation. Okay? Ordinarily, you say, well, how could, you know, something in the visible wavelength or the infrared wavelength give off something that's higher frequency? Well, if you heat things hot enough, you start getting to fusion plasma temperatures, and that would produce the sharpest X-ray images ever taken, because you basically have the spot size that was the smallest spot size possible, or that anyone's ever achieved. But it's hugely expensive, not practical. It's just something that's been done in a national lab. Well, in ultrasonics, you have a spot size, and that spot size is the size of the transducer. So now you got a trade-off. You can either go to bigger transducers that have more energy and have greater ability to detect, but then they're not going to be as sharp because the spot size is not as fine. Well, if you have the wavelength of your radiation is much smaller than the spot size, you come in with a very sharp directed beam. In your ultrasonics, it's just like taking a searchlight, pointing it around. You may have some small side lobes, but the lost energy in the intensity, this is supposed to be a plot, a polar plot of the intensity of the beam. But basically, this is a sharply focused beam when you get a reasonable distance away from spot size. Okay, if this is your source, and basically delta is something, well, delta is officially the width of the source. Once you get 1 or 2 deltas away, you get way out here, you have a nice sharply focused beam, and you can kind of point it around your object. Okay? In here, I've got radiation coming from here and here and here, and so the actual polar plot of intensity inside what they call the near field region gets to be really messy. Okay? This is a plot of the intensity in the near field. This is when lambda is equal to delta. This is when lambda is greater than delta, and you go from a sharply focused beam to a mostly still focused, but losing some sharpness. And then you get over here, if you're trying to measure in the near field region, well, what is the near field region? Well, if you're at a couple of megahertz, the near field region might be something on the order of a millimeter or 2. So it turns out ultrasonics are not very good for detecting small flaws on the surface. Now we have other techniques to detect small flaws on the surface. Ultrasonics are really best for measuring several millimeters below the surface. Okay? But that's just because this is the near field, and this is the far field, and this is the transition in between. You don't have to remember too much of this other than to remember that there is a difference between near field and far field. in ultrasonics. Ultrasonics can't measure right at the surface. And understanding wave propagation in solids is a lifetime study in itself, and it gets very, very complex. Fortunately, all we really want to know is whether we lost ultrasonic signal or not. Okay, did you get, did the beam go through without losing, being attenuated a whole lot? However, there are plenty of people who are trying to use, and actually some people who are using ultrasonics for much more sophisticated purposes. So it's still a very active area of research to try to see what you can really extract from this very complex process. Okay, the next thing I want to talk about was penetrant inspection, sometimes called PT. So we've actually, the people in the non-destructive testing field like to talk about RT, which is radiography testing. They'll talk about UT, which is ultrasonics. They'll talk about PT, which is penetrant. And under penetrant, they actually will call LP and MP or MP. And this means penetrant testing. This means liquid particle. This means magnetic particle or magnetic testing. Okay, there are other types of magnetic testing too. So it gets a little fuzzy sometimes when people start using these this type of notation, exactly what they're talking about. It's not generally too unclear. Let's talk about liquid penetrant testing. First of all, liquid penetrant testing can be used on virtually any material. If it's got a crack, and the crack comes to the surface, all you need to do is find a liquid that will wet the material and be pulled into the crack. The cracks are usually small, and therefore, if it wets, it actually will be pulled in by capillary attraction. Okay? So typically, you can buy a little liquid penetrant testing kit for 60 bucks. It's got half a dozen cans of aerosol, and two of those cans typically might be, 2 or 3 cans might be what they call the cleaner. Well, the cleaner is just a solvent, okay, a degreaser, if you will. You have to be careful to make sure some of these things are because you're going to be testing welds, and you might test a weld that's not complete. If you've got a heavy section weld in some shops, and the weld cross section looks like this, you might build up some weld like this and actually come in and do a penetrant test before you finish the weld. In which case, you may leave behind some of the residue from one of these 3 components of the penetrant testing. You better make sure that that stuff is not harmful when you later melt weld metal and electric arc on top of it. So you like to have things that are chlorine-free. If you're doing steel, and the reason you want chlorine-free is because steel has got carbon in it, oxygen is in the air. If you have chlorine present in the plasma, you will form a compound carbon, oxygen, chlorine. Anybody know what that's called? It's called phosgene. Anybody know what phosgene gas is? It's one of the gases they used to gas people in World War I. Okay, it's a very toxic gas, and it's a fairly simple gas. But if you have in your liquid penetrant materials a material that has chlorine in it, you can have problems. On some of your stainless steels, the chlorides can create problems. You also want to be sulfur-free for a lot of your steels, okay? Because sulfur can cause cracking in welds. So many times, well, for nuclear power plants and stuff, they will have a special grade of penetrant materials that's chlorine and sulfur free, typically because you're a lot of times doing things on stainless steels. One of the advantages of LP is it can be done on any material. Magnetic testing can only be done on ferromagnetic materials. Now, ferromagnetic materials are iron-based, not all iron-based, but I mean, not all stainless steel is. Austenitic stainless steel is not ferromagnetic, but ferritic is, and martensitic is stainless steels. Iron base, cobalt base, nickel base, and the other ferromagnetic element is gadolinium, which we don't have a lot of structural materials made out of gadolinium. But in any case, the advantage of magnetic particle is that 95 pounds out of every 100 pounds of metal made is steel, and therefore magnetic particle is used a lot. But liquid penetrant can be used with aluminum, titanium, anything you want, ceramics, to look for things. And the liquid penetrant basically goes into the crack. If you have one of these simple little tests that you basically spray on a cleaner to clean the surface, then you spray on a typically red dye, and you let it sit for about 15 minutes to give it time to soak in. Then you take the cleaner and you clean off the dye. So this is the liquid dye that goes into the crack. You can wipe it off, but then you typically will spray clean some of that. And then you put a developer on, and the developer is just kind of a white powder that you spray on. Again, it's in one of these aerosol cans. You spray it on, and it will soak up some of the dye, so you'll get essentially a red dye on a white background for that type of liquid penetrant. There are also liquid penetrants that you basically clean the part, you just immerse it. This is typically factory type stuff, and it'll have fluorescent particles in the dye. So it turns out you don't even have to clean the stuff off the surface. It'll just kind of drain off. You basically soak it in there for 10 or 15 minutes, and then you pull the stuff out, and you might kind of shake it down a little bit to get rid of some of the stuff. But then you take an ultraviolet light, and if you've got a crack, you'll have a concentration at the crack of fluorescent particles, and you'll see lines shining back at you. So there are various techniques. If you look, this is a ASTM standard for reference photographs of dye penetrant inspection. This is one with a little red dye on the white background, and there's some cracks there. Okay. Most of the rest of these are the fluorescent type of stuff, and it'll show up white in a photograph. It's not easy to photograph these things because you're basically taking pictures in the dark. There's not a lot of light. In fact, if you go into a fluorescent penetrant, in fact, that's another thing. People call it FP or fluorescent sometimes. The genealogy of these names used to be a little confusing because it's not clear. It's not a standard genealogy, but fluorescent particle or fluorescent penetrant testing, or FP for fluorescent testing, you go into a shop and they'll actually have a little booth with some curtains to kind of keep the light off, so that it doesn't have to be real dark. It's not like a dark room, but it does have to be, you can't have just kind of regular fluorescent lights around. But those processes work for any material. Now, magnetic particle, here's a picture of one of the red dye type of things. This is some sort of impeller or whatever, where they were looking for a crack. So you can see the white stuff that was sprayed around it, and there's the red dye that kind of marks it. Now, just because you get a red mark, it's an indication. Remember yesterday I talked about indications versus real flaws? You have to figure out whether the indication is relevant, whether it's a false indication. A lot of times you just have scratches on the surface. Okay? And scratches are not necessarily a relevant type of flaw and are not a defect. Okay, magnetic testing, on the other hand, there's lots of ways to magnetize something that's ferromagnetic. Maybe I'll start with this one. Let's start with this one before we go to that. Basically, anything that can be made ferromagnet, anything that's ferromagnetic, if you just look at a ferromagnetic material, it have a north pole and a south pole, and there are flux lines that go around that. If you ever played with the iron filings of the magnet, that's basically what you're measuring is the flux lines. If you have two of these, then you have a more complex flux field. If you align the poles so that they're repelling, you'll have a different set of things. But if I basically magnetize something that has a notch in it or a crack, I will get a north and south pole, and I'll have flux lines that, in a ferromagnetic material, you have the potential to have about 10 times the magnetic field density in the ferromagnetic material as you do in the air surrounding it. So you try to saturate the material with magnetic field, and if you have a notch or a defect, and it doesn't have to always be exposed to the surface, it can be just below the surface, then some of those flux lines will, in order, since you've gone to saturation, you're near saturation up in this region where everything's solid, but you get over here and the flux lines get too crowded, you get to too high a density as they're all trying to go around that corner, and some of them have to find their way outside. So some of the magnetic flux escapes outside the part into the air, and that non-uniform magnetic field is going to attract magnetic particles. So you either dip it in a bath that's got some magnetic slurry powders in it. These are like 1 micron, or these are pretty fine particles. But it's basically just iron oxide. Or you can dust it in the field. They have these just little squirt bulb. They probably charge you 15 bucks for it, but if you go to the hardware store or the drugstore, these kind of ear irrigator type of things, just a little squeegee type of thing. And you squirt a little bit of iron powder on the thing while it's magnetized. So, yeah.
One application I know in automotive is like if your engine overheats and you crack your head, they do what they call magnafluxing. You crack your head and you just...
Magnaflux is a trade name.
Right.
Okay. It's the largest company in the world for magnetic particle testing. But yeah, it's magnafluxing, and as long as it's ferromagnetic material, cast iron, that's the head. It doesn't work on aluminum head, right? So you got to use liquid penetrant. But this is magnafluxing in a case like that. If you take the head off, and you're in the shop, you dunk it in a bath, or actually you don't necessarily dunk it on a bath. Typically, what you might do is you have something that looks sort of like a lathe, and it'll have these copper mesh on either end, and you just clamp it in there, and you actually pass an electric current through it to magnetize it. And then they'll have in their little chamber, this will be in a kind of a chamber with some, in the shop with some curtains around it, and they'll flush it with the magnetic particle fluid. And while it's magnetized, well, just like the little iron filings congregate around the child's toy magnet, well, they congregate around the flaws, and so you'll see the cracked head. It just glows back at you, and they use ultrasonics. They use fluorescent particles that are ferromagnetic in some cases. They also, in the field, use dry particles. Okay, just because it's a pain to have liquid sometimes. In the field, you just kind of you magnetize it, and I'll show you that. Did you have some other comment?
No, this is really cool. Like,
yeah,
I mean, it sucks when you have a cracked head, but it's pretty cool. It's a magnet.
I had a cracked head once. No, I did on my car, and it was that's not a story. Well, to magnetize something in the field, you can't just clamp it between this lathe and the shop, but for small parts in the shop, this is a very effective technique. In the field, you may go with what we call prods, and basically you just have a power supply. It's much lower voltage than a welding power supply, but it's very high current. Some of these things will put out 10,000 amps for really big pieces of equipment. You need lots of amps in order to get magnetic saturation on big heavy pieces of steel. But others, like a simple half-inch or 1-inch thick weld, you can go in there with these magnetic prods, and they're just copper or carbon rods that you come down and you touch to the part, and you pass a current through the thing. Now the current might be 1,000 amps. The power supply may not be any bigger than this, because you're only talking a couple of volts, because it's basically sort of a dead short. Okay, you're just trying to put a bunch of current through there. If you put the proper amount of current through here, and you get this thing saturated, then you know what you're doing, and the operator has to change the locations of his prods. He might go like this, they might go like that, he might go like that. He might go over like this. The operators have been trained in order to get high magnetic fields, and you kind of need a third hand, and so sometimes you actually have 3 people or 2 people operating this. One person has to hold the prods on, the other person has to squirt the little dry powder on there in the area where you're looking for the crack. You got to have the magnetic field oriented the right way in order to see the planar defect. Okay, and that's why they have to move these things around. There are also what they call yoke assemblies, which is nothing more than something that has 2 prods, and you kind of take the inverted U, and you kind of, one person can hold that down and squirt with, so you only need 1 person. So whether you're using prods or yokes, you basically pass the current through, generate a magnetic field, squirt some powder on there, and very, very effective at picking up all kinds of flaws in ferromagnetic material. In fact, for something like fillet welds, which for structural materials is one of the most common type of welds. In fact, I would venture to say that something on the order of half the welds made in structural materials are nothing more than fillet welds. Because you've got two pieces of material intersecting at something around 90 degrees. The structural welding code actually tells you within a certain angle, angular variation, whether it's considered a fillet weld or whether it's considered a groove weld. A groove weld is between 2 pieces of material in the same plane, but obviously if you're a little bit out of the plane, does that become a fillet weld, or is that, there's actually a definition, I can't remember what the angle is, it's something like 30 degrees or something between that defines a fillet weld versus a groove weld. Anyway, a fillet weld is just a weld in the corner. Typically, there is no, you sometimes have what they call full penetration fillet welds, but in other cases, you actually have a notch right there in the center where you never welded the material. If you have a fatigue situation, that is a stress concentrator, and you might end up with a fatigue crack growing from inside out. But if you don't have a fatigue situation, it's just a simple building, you don't need a full penetration weld. This is a very simple weld to make because the welder has to lay his metal down in a V groove, basically. Might not be oriented perfectly with gravity, but it's easy. It doesn't take much skill. It's very easy to get the weld down in the bottom of the V. That's why they design fillet welds so they're cheaper to make than a groove weld, where you start out with something like looks like this, and you lay it up and end up with a weld that looks like that to make another, make a bigger plate out of 2 smaller plates. So fillet welds are the most common. Groove welds are easily tested by ultrasonics or X-rays. You get a projection through here, you can bounce a beam through here, you basically have homogeneous, uniform material. This is a pain in the neck to do ultrasonically or with X-ray. You got different thicknesses for X-ray, so you can't get a very uniform exposure. With ultrasonics, well, gee, where are you going to bounce the wave in here? Okay, it's too complex a geometry. So typically what they will do is they'll do magnetic particle. And what you're looking for usually are toe cracks. A crack that comes right down at the toe of the weld and runs into the material. And magnetic particle loves something like that. Okay, you know the orientation of the crack. It's going to be running right along the toe of that weld in 3 dimensions. I'm trying to go into three dimensions here. Right? So magnetic particle, we talked about different levels of inspection. For a bridge or a building, the simplest level, unless you specify something else according to the structural welding code, is you always have to do visual. Then they might, on a more critical weld, specify for steel buildings magnetic particle. Or for aluminum structures, they might specify penetrant testing. Penetrant testing basically is the same type of thing as magnetic particle. You just have to go in there with the spray cans to do the penetrant testing. But it's often fillet welds, and you're often looking for cracks at the toe of the weld. Although aluminum, and this is the stuff I haven't gone through this year, aluminum has problems with centerline cracking and what they call crater cracking at the end of the weld. If the welder doesn't do it properly, aluminum has a much higher solidification shrinkage than steel. And therefore you'll tend to get, as the material shrinks, you pull the weld away, and you shrink, you'll get a cavity called a crater. Okay? Like a crater on the moon. And you'll get cracks there because the residual stresses, as that thing cools, you end up with high tensile stresses right at the bottom of the crater. You also, in different aluminum alloys, end up with liquid metal cracking as the thing cools down. But crater cracks can be a problem. So if you're welding structural aluminum, you're doing penetrant testing, yeah, you're going to look for toe cracks, but you're also going to look for centerline cracks, and you're going to look for crater cracks at the end of the welds. It turns out that with experience, people come to know where to look for flaws, just like I talked about inspection. If you're looking for a flaw and you have to go with a 10x magnifier to look for really small flaws, you have to tell the person where the hot spots are, either from a stress analysis or experience. Well, experience tells us that 90% of the defects in arc welding occur at the stop-start locations. So the stop-start locations are probably only a few percent, probably less than 5% of the total length of the weld, but they constitute 90% of the defects. Okay? Just because the heat flow and everything else is non-uniform, it's a transient condition, and it creates all kinds of problems. The last inspection technique, not the last of all possible ones, there are literally dozens, if not hundreds, of non-destructive testing techniques. But another common one that's used is eddy current. And if you go to Radio Shack and you buy yourself a magnetic detector to take down to the beach to see if you can find some old beer cans or something, except old beer cans, they don't make steel beer cans. The magnetic detectors are best on electromagnetic material, but eddy current works even on anything that's conductive. So it should pick up aluminum and stainless steel and others. It just doesn't have as great a sensitivity. But you can buy these metal detectors at Radio Shack, and I guess people like to go out in the woods or down to the beach and see if they can find some lost treasure, right? Well, eddy current in its simplest form is just a loop of wire that creates an alternating magnetic field, and the magnetic fields might be operating anywhere from a few thousand hertz typically to 100,000 hertz or a couple 100,000 hertz, depending on the size of what you're trying to measure. And this alternating magnetic field next to a conductor by Lenz's law, Lenz's law, isn't it? Is going to induce currents in the conductor, because if I have an alternating magnetic field in a material that conducts electricity, it's going to cause its own electric current. So what you're going to do is use this probe field, and then you'll have a second coil which is going to try to detect the magnetic field. And if you have any discontinuity, what they're showing down here is a little discontinuity, and the magnetic field, or the current going through there, is non-uniform, that's going to give you a magnetic discontinuity similar to the magnetic particle testing, and you can pick that up. Now, the advantage of eddy current over a magnetic particle is eddy current can be operated at 100 kilohertz. That means that you can test things very, very rapidly. Now, the problem with eddy current is it's very geometry dependent. So if I have some complex shape, if it's just a straight fillet weld that goes on to infinity here, but if I have an intersection at a corner of a fillet weld, well, the eddy current doesn't really know what to do. Because I'm going to have all kinds of magnetic changes and current variations as the geometry changes. But if I had something that's uniform in 2 dimensions, then I can probe along there. I have to often design a special eddy current probe, because these things have to be within less than a millimeter of the surface. So there's all kinds of problems with eddy current, but when you can use it, it can be very, very effective. When's it used? Well, it's used when you're welding, making steel tubing. You take stainless steel, and I think if you remember, I talked about somewhere here. I talked about U and O pipe. You basically take a sheet of material and you roll it up into a U, and then you turn it into an O, and you weld the seam. Well, if you do that, let's say on stainless steel pipe, you use a gas tungsten arc, or an electrical resistant pipe where you basically use a high frequency induction heater, and you bring the sheets together like this and kind of forge them while they're being heated by an arc, an inductive arc, between there, and you weld the things, you forge weld them together. Doesn't matter which one you do, you end up with a weld seam down a tube. whether it's a piece of stainless steel that's gas tungsten arc welded, or whether it's electrically resistant pipe. And typically the mill might be going at 60 feet a minute, a foot per second. Actually, it'll be going faster than that for electrical resistance and slower than that for gas tungsten arc. Let's just use a foot per second, even though it's on both sides of that. So a foot per second, you can actually have an eddy current transducer because the geometry is not changing. I'm just making a round pipe. And the eddy current transducer, so you can do 100% inspection at the plant of the welds with an eddy current transducer, and you can do it at high speeds. Okay? Relatively inexpensive transducer. Everything's going through all kinds of fixtures and things so that you can get the exact same standoff distance. The problem with eddy current is, in fact, standoff distance. If I have a coil up here, and I have a part, and I have some flaw here, it turns out the standoff distance here and the size of the signal here, or let me say that the magnitude of the signal is both a function of the size of the flaw and the standoff distance. They're multiplied together. And so if you don't keep the distance very, very precise, then you don't know what size flaw you have. And so your sensitivity is going to be changing all over the place, and you'll get false positives and false negatives, and you'll get true positives too. But anyway, so there's always been this problem when you have a simple cylindrical coil. Now, about 10 years ago, a guy named Neil Goldfein over here in the Lee's laboratory, and Jim Melcher, before he passed away, which is about 12 years ago now, decided to come up with a better design for an eddy current type of coil, for eddy current inspection. And they came up with not a simple little cylindrical coil, but something they call a meandering winding magnetometer. And basically, instead of having a cylindrical coil, you basically make an electrical coil that basically is some sort of square wave like this. But now I can change the shape of the square wave. I can have one that is very narrow. I can have one that's very wide. I can change the frequency. I mean, over here I can change the frequency, but that doesn't do too much for me. Here I can get both spatial and temporal. Frequency is temporal resolution. I get spatial resolution by changing the physical geometric wavelength. And so these detectors are bigger, but they can deconvolute. I now have two pieces of information for my signal, and I can separate out the effects of distance and flaw size, because I now have both temporal and spatial resolution to this type of geometric design of my magnetic coil. And so it turns out it's a very powerful technique, and I was just leading a technology review this month, because Professor Zahn over in mechanical engineering and Neil Goldfein, who started a company, are proposing, or have proposed, for instance, you don't like to take your shoes off at the airport. They have a proposal to essentially use this technique where you would just walk over a meandering winding magnetometer. Just be a rug on the floor, and it would detect whether there's anything in your shoe. Okay, by using essentially an eddy current technique for metals. There's a analog for this for dielectric where you use capacitive techniques. Okay, and that was one of Professor Melcher's other doctoral students. One of the things you have to worry about those things is something called penetration depth. For different materials, depending on their electrical conductivity, you'll get sensitivity down to different depths in the material. So one material may have a shallow penetration depth, another material may have a big penetration depth, and it has to do with the electrical conductivity of the material. And so there are plots of depth of penetration versus frequency for these different things. That's called the skin effect for any of you electrical engineers. So there are a host of non-destructive test techniques. Remember, non-destructive testing quite often can be equal to the cost of fabrication, the welding. In really critical materials or structures, the non-destructive testing can be 2 or 3 times as great as all the other fabrication costs. And it has to do with what type of quality you require. People talk about Six Sigma. Well, back 10 years ago when we had the problems with the Hubble telescope, remember they mismachined it, they sent it up there, and they spent $2 billion to get it up there, to build it, to get it up there, and find out it had astigmatism. And they did finally correct it, but it cost them, I think, well, it cost them about $1 billion to fix it, because it cost $500 million just to send the space shuttle up with the repair stuff. And I'm sure they probably spent hundreds of millions more on figuring out what the repair was. Well, I used to say, you know, is Six Sigma good enough? Well, it depends on what you're building. If you're making bricks, 3 Sigma might be good enough, because you know, a cracked brick is not a big deal. If you're just going to build a wall, you'll probably see it, and even if you had a crack in one brick, the wall's not going to fall down. In fact, if you go back 10 years later, you'll find a few cracked bricks, okay, just because they're ceramics, they break. If you're building Hubble telescopes, you may need 9 Sigma in terms of the quality that you're trying to design in. You're going to try to design it in, you're going to try to get it in by process, and then you can try to inspect it in, which is the least desirable way, but still a way that's done a lot of times. Unfortunately, in the Hubble telescope, they didn't do quite enough inspecting in the quality, and the stuff got out because of that. And it cost a lot of money. But it just depends on how critical something is. The Hubble telescope wasn't life-threatening, but it sure did cost a lot of money to make that type of mistake. Okay, thank you very much, and I'll be, turn it off.